Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture number 9 of the course Introduction to Robotics. Today we'll talk about inverse kinematics of the PUMA manipulator. In the last class we looked at inverse kinematics of a 3 degree of freedom planar arm. Then we looked at the inverse kinematics of the SCARA robot, and we'll today move on to inverse kinematics of 6 degree of freedom PUMA robot. So today we talk about the inverse kinematics of the PUMA arm. Now very briefly to revise, what is the inverse kinematics problem? So the inverse kinematics problem is given the desired position and orientation. So the position plus orientation of the end effector. We want to find what are the corresponding joint angles and these, which are the variables, right? In the case of revolute joint or a prismatic joint system. This is my inverse kinematics process. Now let's look at the basic process that is followed. The basic process that is followed for all manipulators is the same. So for 2 degree of freedom or 3 degree of freedom system, which we looked at, is we assign our, so the first thing that we do is to assign axis. So we assign axis, okay, as per DH notations. That means that axis of rotation, x-axis is the shortest distance between the z-axis. Then what we do is we make our transformation matrices. So transform matrices, okay, so which relates one axis to the other axis. Then we multiply them out and find the total transformation from the 0 frame to the nth frame. Okay. Then there is a desired position and orientation of the end effector. Which is given to us. So this we can call as the desired position and orientation. This is my rotation matrix. This is the position. This is 0, 0, 0. That is 1. So what we do is we equate the T0 to n to the desired position and orientation of the end effector, and then equate term by term and try to solve. So then we equate terms and solve. Okay. Now what we have seen in the last, in the case of this 3 degree of freedom system, is that it is difficult to try and solve from here, because there is a cos and a sine term which comes in all kinds of orders. So it is a cos 1, 2, 3, which means cos theta 1 plus theta 2 plus theta 3. So equating that to the right hand side term, it is not possible to solve. So we start solving normally from the position terms. Now let's look at the case of the PUMA robot, which is a 6 degree of freedom robot. Now, the first thing that we do is we assign our axis. Now the axis has been assigned. In the forward kinematics, I explained how the axis was assigned, and then we make our DH parameter table. So again, going very quickly to our DH parameter table, what we do is A alpha, D and theta. So we have A alpha, D and theta, and there are 6 of them. So there is 1, 2, 3, 4, 5 and 6. Okay. And the terms which we got, the first one is 0, 0, 0, theta 1. So you can see the first frame, 0 frame and z1 frame are the same frame, and they are intersecting at the point x. Okay, so 0, z0 and z1 is the same frame, and hence it is, the first term is 0, 0, 0, theta 1. The next one is the z is rotated by 90 degrees. Okay, so it is a minus 90 there. So z1 has become z2, and that is a minus 90 there. This is 0. The origins are still the same, so this is A is also 0 and this is 2. What about the third frame? Now there is a distance of A2 in case of the third frame. So we have A2 distance, which is here, the distance between the Z1 and Z2. No, sorry, Z3 and Z2 is A2. Now Z3 and Z2 are parallel, so this is 0, and but there is a slight shift. The third origin is here, so there is a shift of D3 here. Okay, so basically the origin 2 moved this way and then it moved forward like that. So this is my A2, and that is my D3. Okay, that is how it came. So this is my D3 here, and this is theta 3. Now for the fourth one, we go to the wrist, and you can go to the figure on top. So my third axis is in that direction. So that's my that's my Z3. So that is my Z3, right? Now where is the fourth axis? The fourth axis is this way. So this has rotated by 90 degrees clockwise, and hence it is minus 90 there. Now there is a distance of A2 between the Z-axis. So this is my A3. So A3 comes here, and there is also a distance of D4, which is the distance between the x-axis, and my variable is theta 4. Okay, so this is my this is for the fourth joint. Now for the fifth one, what we see is that the x-axis, z-axis is on that side. So this is my Z5. Okay, x4, x5, x6 are on the same axis, the same direction. Z4 is the roll axis. Now Z5 is that side, so it is rotating anti-clockwise by 90 degrees. So this is 90 degrees, and there is no distance here. So these are all 0, 0, and there is theta 5. Then again, Z5 becomes Z6. Z6 is in this direction only. So you can see Z6 is in this direction only. Okay, so this rotates clockwise now about x. So it is a minus 90. And this is 0, 0, theta 6. Now something very important to note here is that for many manipulators, if you just multiply out 0 to the transformation matrix T0 to 6, okay, equated to the desired position orientation matrix, okay, you may not be able to solve. Now in this particular case also, we are not able to solve. So what it means that if I find the link-to-link transformations, multiply them out, and then try equate it to the desired position orientation of the end effector, and then try to solve equation by equation, we will not be able to solve for this kind of manipulator. Now, so the solution for every manipulator could be different, or you have to be very, very observant to see how the equations are, and then try and solve. So here is something that we note in this manipulator, is that after link number axis number 4, which is here, okay, there is no change in A or D. Why? Because the last three axes are intersecting. So please note that last three axes are intersecting. Okay, so this is something that we need to note here. And because this last three axes are intersecting, there is no change in the origin, position of the origin. For so origin of 4, 5, and 6 are the same. Now because of which the equations, when we multiply T0 to 6, they have a particular structure, and that is something that we are going to exploit when we are going to try and find the inverse kinematic solution. So we write our matrices. This is something I had done in the last class. So we simply take the generalized transformation, which takes us from one frame to another frame, and from the DH parameter table for each of the rows, what we do is we put into the generalized matrix, and we get the transformation from 0 to 1, 1 to 2, 2 to 3, like that up to the end. Okay, so these are giving us the individual matrices which are taking from one axis to another axis. Now what we want to find is the frame T. So what we want to find is this frame T0 to 6. Okay, but if we do this, we find that the terms that come for all the elements, they all contain sine and cos terms, and from there it is not possible to solve. Okay, so what we do is we multiply in a particular way. That means this multiplication, which is equal to T0 to 1, T1 to 2, T2 to 3, T3 to 4, T5 4 to 5, and T5 to 6. They can, each of this matrix contains one variable, this theta 1, theta 2, theta 3, theta 4, theta 5, and theta 6, right? Now we observe that if you multiply in a particular way, okay, then it is possible to solve, and that is the procedure that we are going to follow here. So we will not multiply them straight out like this. So what we'll do is first we will multiply 4 to 6. So we'll multiply this one first, then we'll multiply 3 to 6, okay, then we're going to multiply 3 to 6, then we're going to multiply 1 to 3. Okay, so when we multiply it like this, a particular structure appears, which is which helps us in solving the equation. As we go along, it will become clearer. So first of all, what we do is we multiply 4 to 6, Okay, 4 to 6 is this one. T4 to 6 is the first one. T4 to 6 is the first one that we multiply, which is equal to 4 to 5 and 5 to 6. 4 to 5 and T 5 to 6. So we have seen what these matrices are. So if you just multiply them out, what it gets, C5 C6 minus C5 S6 minus S5, this becomes 0, and this becomes S6 C6 0 0. This becomes S5 C6 minus S5. This becomes minus of S5 S6. So the two variables are theta 5 and theta 6 that you can see. That is 0, this is 0 0 0 1. Let's call this equation number 1. Okay, so this is one multiplication we have done. Now then what we do is we do 3 to 6. 3 to 6. 3 to 6 means equal to 3 to 4. T3 to 4 and multiplied by 4 to 6. 4 to 6 we just got. Now if I do multiply this, then what we get? What we get is C4, C5 and C6 minus S4 and S6. The second term is S5 and C6, then it is minus S4, C5 and C6 is the first column. The second column is minus C4, C5 and S6 minus S4, C6. The second term is minus S5 and S6, and here it is S4, C5 and S6 minus C4, C6. And this is C4 and C6. The third column is C4, S5, C5 and S4, S5. This is A3. This is D4. This is 0. This is 0. 0 1. Okay, let's call this equation number 2. So what we did is we first multiplied this, then we multiplied with this. Okay, you'll understand why. Now, so this is one set. 3 to 6 is one set. So 3 to 6 is one set that we have multiplied. The other set that we are multiplying is 1 to 3, T1 to 3. So we just take those 1 to 3 matrices and multiply them out, and what we do get is we get C2 to 3 minus sine 2 3 0. This is A2 C2. Here it is 0 0 1, and it is D3 here. Then we have minus 2 3 minus cos 2 3. This is 0. This is minus A2 S2 0 0 0 1. Okay. Now this is my 1 2 3. So what are the variables here? It is theta 1. Sorry, it is theta 2 and theta 3. So it is theta 2 and theta 3. Okay, what are the variables? Theta 2, theta 3. The previous case, what were the variables? It was 4, 5 and 6. So the variables is theta 4, theta 5 and theta 6. So there are 3 variables here. And here there are 2 variables, theta 2 and theta 3. Okay. Now we multiply the complete T1 to 6, which comes out to be equal to 1 R11, 1 2 R13. These terms are very large, so we're just writing them in PX1, R21, R22 and R23 PY. This is R31, R32 and R33 PZ, and the last row is of course the same, always 0 0 0 1. Now this is 1 to 6, so we are putting the subscript 1 here. Okay, so the subscript 1 essentially indicates it is 1 to 6. Now each of these terms, if you see, what we see is that they appear like this. Okay, so R11 is equal to cos 2 3, cos 4, cos 5, cos 6 minus sine 4, sine 6 minus sine 2 3, sine 5, sine 6. And you can observe that all the terms have sine and cos except this term. This is a z here, pz. Okay. So basically what we are seeing here is that all the terms contain sine and cos, and there is only one term there that does not contain. So there is no sine or cos here. Okay, so this is something to note. Okay, so this basically means that if you try to solve from somewhere else by using some other term, comparing left and right, you'll not be able. Whereas in this particular case, because there is no sine cos here, we may be able to solve from here. And that is the reason why it was multiplied t1 to 6. So what is not there is t0 to 1 is not there. Okay, that. So it basically means that if you're multiplying in a particular way, if I'm multiplying 1 to 6, then we end up in this structure and we end up with this term py, which is not having any cos and sine terms. But if we proceed and multiply t 0 to 6, then what happens is you end up with this matrix, which is R11, R12, R13, R14, and this is R21, 22, 23, and R24. Here it is 31, 32, 33, and 34. This is 0, 0, 0, 1. Okay. Now the terms of this, each of this are given here. Okay, so these are the terms that come if you multiply 0 to 6, and you see that each of the elements, all of them contain sine and cos terms, and there is no element which does not contain a sine and cos term. They contain sine and cos terms, but they also have very complicated terms. For example, you can look at this term, which is having cos 1, cos 2, 3, cos 4, cos 5, cos 6, then sine, then again sine, cos. Look at this term. How many of the variables and in what order? So it's almost impossible to solve by equating these terms. Okay. So basically what we are doing is we are multiplying it in this order by trying to remove that, we are trying to remove the 0, the 1 to 0, and then observing that we end up with one term which does not have sine and cos, and that is where that is how we start our inverse kinematic solution. Okay. So now if you want to remove that first term, how do we remove it is like this. So what we do is a very interesting way of trying to solve this. So we have t0 to 6 is equal to r11, r12, like that. Okay, so this is something we have seen. Okay, the matrix we just saw. This is 0, 0, 0, 1. Okay, so this is r12, 13, and 14. Okay, sorry, this is px. In the previous one also, I think I made that mistake. Yeah, so this is px, py, pz. Sorry. So this is px, py, and pz. Okay. So what we do is, this is my px, py, and pz. Okay. So what we do essentially is, if you want to remove theta 1 from here, what you'll do is we take theta 1 on the other side. Okay. So what I do is I remove theta 1 and take it onto the other side, which means that this is equal to t0 to 1, t1 to 2, like that, up to t5 to 6. So if I want to remove this one, what do? I take the inverse and I bring him this side. Okay. So what we are doing is I'm doing t0 to 1, which contains theta 1, inverse, multiplying this with t0 to 6. Okay. And what will be left on the right side is t1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. So what we are doing basically from the right hand side, I'm removing theta 1, bring it on the left side. So the variables here are theta 2 to theta 6. Theta 1 has gone on this side now. Okay. So what we do here is, now what was theta 1? Theta 1 inverse, theta 1 was cos, sine, cos. If you remember what was the first matrix. So the first matrix t0 to 1 was cos minus sine, cos, 0, 0, 1, 0, 0. This was 0, 0, 0. This was 1, 0, 0, 0. So if I take the inverse of this, what we get is the inverse of this comes out to be sine cos 1 sine 1 minus sine 1 cos 1, 0, 0, 1, 0, 0. This is 0, 0, 0. This is 0, 0, 0, 1. Okay. And here we have R1. So here we have R11, R12, R13, PX, R21, R22, R23, BY, and R33, R31, R32, sorry, R31, R32 and R33 and Pz. This is 0, 0, 0, 1. Let's call this equation number 3. Okay. So I hope you understand what we are doing, that essentially we are removing the theta1 from the right hand side and bring it on the left hand side now. Okay, and this is equal to T1 to 6, and I know what is T1 to 6. T1 to 6 does not contain on the term on one of the terms, it does not contain the any sine and cos term, right? That is what we're trying to do. So from here we are trying to solve now. Okay, so we multiply this into this, equate it to 1 to 6, and then try and solve. That is the way we are going to proceed. Okay, now so what we do is equating. So the first solution, what we're trying to do is equating 2 to 4 terms of both sides of equation 3. So this is my equation 3. Okay, so this is my equation 3, right? Now 2 4 terms will mean 2 and 4 means y, py, right? So it is this one into that one into this row. So the 2 4 term would mean this into that. Why? Why are we doing that? Because you observe that this term, which is the 2 4 term, actually does not contain any sine and cos. Okay, so we're trying to target this term now. So what we are doing is we are multiplying the 2 4 terms of this equation. So second row and 4 is this one. Okay, the fourth column. So we'll be ending up with this term for py, and you know what was py there? It was d3. So basically, if you multiply that in equation 3, okay, equating 2 4 terms of both sides of equation 3, what we do get is minus sine 1 px plus c1 py is equal to d3. Okay, so we have got an equation which contains only sine 1 and cos 1, and d3 is a constant. Okay, so from here we can make the substitution. Px is equal to rho times cos phi, and py is equal to rho times sine phi. Okay, where rho is equal to root over px squared plus py squared, and phi is equal to a tan 2 px py. Okay, now if you make the substitution, we can solve and get theta 1. Theta 1 is equal to a tan 2 py px minus a tan 2 d3 plus minus root over px squared plus py squared minus d3 squared. Okay, so now we have found one of the variables, which is theta 1. Okay, now next what we do is we target this equation again. Okay, we target this equation number 3 again, and then try and see which terms we can solve by equating left hand side and right hand side. Okay, so next what we target is the 1 4 elements and 3 4 elements. So we target 1 4 elements. So we equate 1 4 and 3 4 elements, okay, of equation 3. Okay, so we go back to our equation 3, which is this one, and we target the 1 4 element. So 1 is this one and 4 is that side. So 1 4 and 3 4 elements. 3 4 is this, 3 is this one row, and 4 is this one. So what you'll be getting is pz here you'll be targeting. So you'll get 2 equations with 2 variables, and then we can try and solve them. Okay, so what is done is we are targeting 1 4 and 3 4 elements of equation 3, and what we are getting is c1 px plus s1 py is equal to a3 c23 minus d4 s23 plus a2 c2, and the second equation we get is minus of pz is equal to a3 s23 plus d4 c23 plus a2 s2. Okay, so we get 2 equations, and there are 2 unknowns. What are the unknowns? One is theta 2 and the other is theta 3. Okay, and theta 1 is already known, so cos 1 sin 1, theta 1 is already known. So what we do, if we square equations and add, if we square this, squaring and adding squaring and adding. Okay, what we get is A3C2 minus D4S3 is equal to K, where K is equal to, so K is equal to Px squared plus Py squared plus Pz squared minus A2 squared minus A3 squared minus D3 squared minus D4 squared divided by 2A2, right? And from here we can find theta 3 to be equal to, we can solve theta 3 as a tan 2 A3 D4 minus a tan 2 K plus minus root over A3 squared plus D4 squared minus K squared. Okay, so we have solved for theta 3. So we had found theta 1, now we found theta 3. Now what we do is we again proceed and try and see that we have to look at the order of the multiplication which we had done and what terms we can get out which do not contain sine and cos. So what we do is we again go back here and write it this way: t0 to 3, okay, containing theta 2 is equal to inverse of this multiplied by t0 to 6 will give us the matrix t3 to 4, t4 to 5 and t5 to 6. Okay, we said that we are multiplying in a particular sequence. First we did, if you remember, 0 to 3, and then we did 4 to 6, okay, and then we removed theta 1. So now in this matrix theta 1 and theta 3 are known. So what is not known is theta 2. So theta 2 is unknown now. So on the left hand side you have one unknown. On the right hand side you have theta 4, theta 5, theta 6. Okay. So now what we do on this, let's call this equation number 4. Okay, now equating elements 1, 4 and 2, 4. Okay, of equation 4. So this is my equation 4. We know what this side is. We just wrote it some time back. We know what this side is. We know this matrix. Okay, so we know we can take its inverse. Theta 1, theta 2 is already known. So if we do this, we take the 1, 4 element and 2, 4 element of this equation. Then what do we get is two equations: C1, C2, 3 Px plus sine 1 cos 2, 3 Py minus sine 2, 3 Pz minus A2C3 is equal to A3. This is one. And the other one is equal to minus C1 S23Px minus S1 S23Py minus C23Pz plus A2 S3 is equal to D4. Okay. And we can solve this simultaneously. So simultaneously we solve these two equations, and we basically get 2, 3 is equal to theta 2, 3. So you see we are getting cos 2, 3 here. So here also it is sine 2, 3. So what we are getting is theta 2, 3 is equal to a tan 2, which is given as minus A3 minus A2C3Pz minus C1 Px plus S1 Py, and this is D4 minus A2 S3. This is my sine term, and the cos term is A2 S3 minus D4 Pz minus A3 minus A2 C3 C1 Px plus S1 Py. Okay, so this is giving me cos theta 2, 3, and to get theta 2 out of this, I need to do is equal to theta 2, 3 minus theta 3. We already have theta 1, we already have theta 3, so I have what is theta 3. So theta 2 is equal to this, so I get my theta 2 now. Okay. Now so what have we found till now? We have found theta 1, we have found theta 2, we have found theta 3. So we have found all these three. Now what we need to do is again we look at equation number 4. So our equation number 4 was this one, okay, and what we do is we equate 1 3 and 3 3 elements of both sides of this. So 1 3 and 4 3 elements of both sides of this we equate, and if you do that, so equating the elements 1 3 and 4 3 and 3 3 of both sides of equation 4, we get two equations again, R1 3 C1 C2 3 plus R2 3 S1 cos 2 3 minus R3 3 S2 3 is equal to minus C4 S5, and here we have minus 1 3 S1 plus R2 3 C1 is equal to S4 and S5. Okay, so this is what we are getting. So just to go back, we are equating the 1 3 elements and 3 3 elements of this. Okay, so what is 1 3, and on the right hand side we have this, right? So if you go back 3 to 6, we have just multiplied it sometime back, 3 to 6 matrix. What was the matrix like? So right at the beginning today we did that. So 3 to 6, this is 1 to 6, so this is 4 to 6, right? So this is the matrix we are looking at, that this is a 3 to 6 matrix. This is my 3 to 6 matrix, which is on the right hand side, right? Now on this matrix we are equating terms 1 3 and 3 3. So 1 3 would be this term, okay, 1 3 is this term, and the other term is 3 3, which is this term. Okay, so on the right hand side these are the two terms, and the left hand side we are multiplying it out and getting it. So it was sine. Okay, that is what we have done. So okay, yeah, so here you can see this is 1 3 term, and this is 3 3 term. The left hand side is this, and right hand side is this one. Okay, so now we have what are the variables involved? Theta 4 and theta 5 are there. Theta 1, theta 2, theta 3 are known. So left hand side is all known. So theta 1, theta 2, theta 3 we already obtained. So left hand side is known. What we are left is with the right hand side now, theta 4 and theta 5. Okay, now how we solve this? Now we can solve this and find that theta 4. Okay, we can square and add and get that this is equal to a tan 2 minus R1 3 S1 plus R2 3 C1 minus of R1 3 C1 C2 3 minus R2 3 sine 1 cos 2 3 plus R3 3 sine 2 3. Okay, so this is what we get as theta 4. So once we have got theta 4, we have finished with theta 1, theta 2, theta 3 and theta 4. Okay, what are we left with? Theta 5 and theta 6. Now again what we do is we observe these equations and find that if you try and remove from the left hand side, okay, that means on the right hand side, if you just keep the variables 5 and 6, and on the left hand side we bring theta 1, theta 2, theta 3, theta 4, because they're all known. So what we are doing basically is we are bringing this matrix inverse of this, okay, on the left hand side, because these are all known here. All the variables here are known. And on the right side we are left with theta 5 and t 5 to 6. Okay, so this is a variable of theta 5 and this is a variable of theta 6. Okay, so this is what we are doing, and what we do here is this I can call as my equation number 5. Now in this what we are doing is we are equating the two elements 1 3 and 3 3 elements of 5 of equation 5. This is what we are doing. So please try to understand the logic, The logic here is that on the left hand side we have theta 1 to theta 4, which is known. Okay, on the right hand side, this is my given position orientation. This is also known. So on the right hand side we have theta 5 and theta 6. We have brought all the theta 1 to theta 4 on the left hand side. So on the right side we only have two unknowns now. So if we equate these two, what we get is this to 1 3 cos 1 cos 2 3 cos 4 plus sine 1 sine 4 plus r2 3 sine 1 cos 2 3 cos 4 minus cos 1 sine 4 minus r3 3 sine 2 3 c4 is equal to minus of sine 5. Okay, you have to go back to that matrix and simply look at the terms 1 3 and 3 3. So we are having two terms and we can equate them. So r1 3, this is minus c1 s2 3 plus r2 3 minus s1 s2 3 plus r3 3 minus c2 3 is equal to c5. Okay, and from here we can solve theta 5 as theta 5 is equal to a tan 2 sine 5 cos 5. Okay, this is our solution of for theta 5. Now in this equation we also know theta 5 now. So what do? We bring theta 5 also to the left hand side. So what will be left on the right hand side is only going to be theta 6. Okay, so this is the logic that we are following, and now we bring 0 to 5 t0 to 5 onto the left hand side. When we multiply this with t0 to 6, we get 5 to 6 t theta 6. Okay, so that means the right hand side only has one variable, which is theta 6, which is unknown. Okay. Now equating both the elements, of this equation, now this is equation number 6. So equating elements of 3 1 and 1 1 from both sides of 6, we get theta 6 is equal to a tan 2 s6 and c6. Okay, so sine and cos terms are already given. So s6 is equal to minus r11 c1 c2 3 s4 minus s1 c4 minus r21 s1 c2 3 s4 plus c1 c4 plus r31 s2 3 s4. This is 1, and c6 is equal to r11. Now what we note here is that all these terms, there are so many terms which are having the sine and cos terms. Okay, c5 minus c1 s2 3 s5 plus r21 s1 c2 3 c4 minus c1 s4 c5 minus s1 s2 3 s5 okay, minus r31 s23 c4 c5 plus c23 s5. Now all these terms here, they contain theta 1 to theta 5. We are already knowing what these values are. We have solved for them. So these values are known, right? And hence from here we can find, hence from this term we can find what is theta 6. Now this is the way the inverse kinematics is done for the PUMA manipulator. PUMA manipulator is industrial manipulator, and all industrial manipulators have inverse kinematics which have to be solved in a particular way. Okay, so it is very important to understand that in general, if you try and solve for a 6 degree of freedom system, you may not be able to solve. Okay, and why was it possible that we were able to solve for this manipulator? That's a more important question which you need to understand. So let's look a little bit into why we were able to solve for this manipulator system, and try to understand what was the basic logic that was used. So the basic logic that was used here is that okay, let me go back here, is that when we are trying to solve, we basically solve the desired, this is my desired position orientation of the interfactor with the t0 to n. So the right hand side is known, so everything here is known. This part is unknown, and this would be having variables theta1 to theta n. These are all unknown. So if you try and go, if you go term by term, we will not be able to solve. Okay, and now, so what was done is essentially we were multiplying it in a particular sequence. Okay, so what we did is we multiplied it in such a way that we first multiplied this. Okay, that is, we did 4 to 6, then we did 3 to 6. Okay, then what we did is we did so this is one set, 3 to 6. The next set that we did was 1 to 3. Okay, so then we multiplied both of them. So we multiplied t1 to 3 into t4 to 6, and then we got this one, 1 to 6. And then what we found is that there is a particular term, okay, here, which does not contain a sine and a cos, only when we multiply it like this. The moment you start multiplying with 0 to 1 also, so this is equal to t0 to 1 and t2 to 6. The moment you do that, you find that this term, which had d3 there, now it ends up with this term which had d3 in the previous case, so py now ends up with so many terms now. And in this situation, you cannot solve, because all the terms have funny combinations of sine and cos, and we will not be able to solve. Okay, so Piper was one of the earliest who observed the structure of this system of equations, and this way of solving is called Piper's solution. So Piper's solution essentially says that you write the so what you do is you write the equation in such a way that the left hand side and the right hand side have known variables, and then you can try and solve. So what we did is essentially we removed 0 to 1 first. So this is what we did. Let's look at what we did again. So from here what we did is we removed from 0 to 6, I removed theta 1. Okay, so on the right hand side we did not have theta 1, and then we try and solve for theta 1. Okay, by observing that this term py is equal to d3. Okay, and then we solve for theta 2, theta 3. So we got theta 1, then we solve for theta 3. After getting theta 3, we solve for the theta 2, then we got theta 2. Okay, then we got theta 4, theta 4, then 5, then 6 in that order. But the most important question here is, why did this structure happen like this? Why is it that when we multiply 1 to 6, okay, that's a more relevant question. When we multiply 1 to 6, okay, so we are multiplying 1 to 6, why does it happen that this fellow does not have any sine and a cos? Okay, that's an interesting question. Okay, now why does that happen? If you think a little bit, you'll have to go back and look at the manipulator structure. So if you look at the manipulator structure and you look at the DH parameter table, okay, very carefully. So if you look at the manipulator structure and you look at the DH parameter table very, very carefully, we see that 0 and 1 axis are here. 0 and 1 is here. 0, 1 and 2, all three are here. 0, 1, 2 origins are there. They are the same point. Frame 3 is here. Origin of frame 3. Frame 4 origin is here. So on this figure here, it is at that point. So origin of 4, 5 and 6 are the same point. Okay. So because the origins of 4, 5 and 6 are the same point, what happens is there is no change in terms of A or D after this point. Okay, so if you look here, your terms here, your A and D, your A and your D are 0. And the only variable is theta 5 and theta 6. And this is happening because those three axes are intersecting at a point. Okay, so the last three axes intersecting at a point is the reason why it is having this structure. So from here we understand that if you want to solve equation, if you want to solve a 6 degree of freedom system, so I'll just write it here. So solving 6 DOF system, okay, requires that, so for a solution or for being or for the system having an algebraic solution, requires last three axes. So this is very important theorem. It requires last three axes to be intersecting. And this method of solving is called Piper's solution. This is called Piper's solution for 60-year systems. Okay. So something very important, that for a solution to exist, for a 6-degree of freedom system, algebraic solution to exist, number one condition requirement is that the last three axes should be intersecting. Now, very interestingly to note that the human axis, the last three axes are not intersecting. So actually human arm does not have a closed form solution, okay, because the last three axes are not intersecting. The two axes at the elbow are intersecting. So the roll and the elbow axis are intersecting at the elbow, whereas the pitch and the yaw axis are at the wrist. So our structure of the arm, the human arm structure, is 3 at the shoulder, then there is 2 at the elbow, and there is 2 at the wrist. So there's 7. Okay, and this does not have a closed form solution. Now the only other exception, there is an exception to this, is if your fourth axis and your third axis are parallel. Okay, so the other exception is if your third axis and fourth axis are parallel. Okay, so if they are parallel and the last three are not intersecting, then also it is solvable. So this will come to when we come to robot design, and we'll talk about design of the wrist. The roll, pitch, yaw, wrist has different designs. So when we come to this design of robot manipulators towards the end, then we'll see that there is an exception to this rule. But in general, for a 6-degree of freedom to be solvable, we need to have the last three axes to be intersecting. So in today's class, we looked at the inverse kinematic solution of the 6-degree of freedom PUMA robotic arm, and we saw that the equations have a particular structure, and we are able to solve because the last three axes are intersecting. If the last three axes do not intersect, then we will not be able to solve this manipulator structure. Now, so you should be able very careful when you're designing robotic systems, that you can design a robotic system, but then if it is not solvable, then it's of no point because you cannot control it. Okay, so this is an important lesson here, and the way of solving it this way was first proposed by Piper, and this is also called Piper's solution. So we will stop here today, and in the next class we'll move over to the study of Jacobians. That is, what is the relationship between the joint velocity and the end effector velocity, because at the end of the day we are going to control the joint velocity. The motor is connected to the joints, so when the joint rotates, the end effector also moves. So what is the relation between them? So that is what we'll study when we look at Jacobians in the next class. So today we'll stop here. Thank you.